Hi everyone, welcome to another chemistry video. Looking at stoichiometry and gravimetric analysis. So this is in chapter 18, 18.2 and point 3. So we're looking specifically at gravimetric analysis, which is one of these techniques that we use to figure out concentrations, and we want to find exact calculations. So it's really linked to precipitation reactions, and it's all about weighing things. So we often use it to look at particular salts, so looking at NaCl or something like that, and we use stoichiometry, which means that we want to be able to look at our chemical equations and then looking at the coefficients in front of them, that we can basically make the law of conservation of mass. Means that you can say that if I have 1 mole of this, then I will definitely have 2 moles of the other product. Okay, so firstly we're looking at the way that we are actually dissolving our sample in water. And so basically you have your sample dissolved in water and you put a chemical in, and you know that you want it to form this precipitate. It's really important that it forms a precipitate, that way you can weigh it and collect it afterwards, and then you can figure out how much you had of your product, and then using the equations you can figure out how much you would have had of your reactants. So it's really important that you end up doing this, and it's got to be determined quantitatively, which is saying it's got to be calculated with exact numbers. And it's also interesting because we end up generally putting it in heat at the very end of it to make sure that there's no evaporation, there's no water left in it. That's the idea. We have a brief look at this diagram. So you can see that step 1, we dissolve our solid, something like a lead something or other, with another chemical species. We put that in water, and so we see that we have our Pb2+ ions and the other chemical species. Then we want to add something with SO4 to negative, so it's a sulfate, because we know that when we have lead and sulfate together, they form a solid. So we see that we have solid lead sulfate with the other chemical species and some leftover sulfate. And then what we do is we filter and weigh it out. And so once you've done those 3 steps, you end up with a product at the end, and that tells you how much you formed, and then because you know your equation, you can figure out what you had at the start. So this is basically just talking you through it. So the question was, how much salt is in baby food? So step 1 is we're going to say weigh it. We've got to weigh how much we have at the start. Number 2 is we're going to dissolve it. Number 3 is we have an excess of the extra chemical, which in this case would be silver nitrate, to the baby food, and so that we have our NaCl and also our AgNO3. And then what happens is that we collect this product here. So we collect our silver chloride because that's a solid, whereas you also have the nitrate, and you also have, the sodium. There we go. So it'll be sodium left over with nitrate, and both of them will be aqueous. Okay, so let's quickly go through a worked example. So if this is the one, it would say infant cereals shouldn't contain more than 3.3% NaCl. So if your exact mass is 7.802 of baby cereal, was blended with water, so put into a solution and filtered. The solution was mixed with AgNO3, and then silver chloride was formed, which is just what we went through. The precipitate was collected, and we ended up with a mass of 0.112 grams at the end. How would we work out whether we had more than 0.03 sodium chloride? Okay, so this is the one from the book, but the idea is basically to write your equation first. That's always the first thing you do, is write your equation, and we can see that we have a 1:1 to 1:1 ratio. When you're calculating the mass, so you know that you've ended up at the end, you've got 0.112, you divide that by the molar mass of silver chloride, because that's your solid, you get 0.000781 mole. We know it's 1:1, therefore we know that when we have, because we've calculated this, so we've calculated AgCl as a solid, because it's 1:1 to 1:1, therefore we know that the mass of NaCl, which is what we're interested in, will be the exact same number of moles. So then we just look down here, we know that our number of moles equals 0.000781, and then we can similarly convert from m equals n times capital M, we times the moles by the molar mass of NaCl, which gives us 0.457. And then I don't think I have the last step, but if you take that divided by your total, which I believe is 7 grams, it's actually less, it's than 0.03%. Okay, so some of the things that we need to think about, which is used for. So gravimetric analysis is useful for finding metal ions, whether that be in food or other things. It's really useful for looking at impurities, such as sulfates, especially sulfates because they tend to combine with most things and then they are forming precipitates. But it's also super useful with water as well. One of the things that we look at is that you've got to make sure that they form stable precipitates. So something like sodium nitrate is always going to be soluble because sodium is part of SNAPE and so is nitrate. So even if you're trying to form that as your end, you're not going to be able to find a solid. Similarly, something like silver sulfate, it's going to be insoluble. So even if you put it in water, it doesn't dissolve. So you need to make sure that you've got things that become aqueous and then will form a solid at the end. Remember that the word analyte is the substance being analyzed. So hopefully you can work that one out, but that one probably needs to just be in your memories. Okay, if you're getting lost, revise chapter 13, because it all basically comes down to 13.4 and 13.3 and precipitation reactions. So there's the page numbers. So SNAPE is sodium, nitrate, ammonium, potassium, and ethanoate, always soluble. And then TROPS is carbonates, hydroxides, oxides, phosphates, and sulfides, usually insoluble, because if you pair them with something from SNAPE, then they will be soluble, but pretty much most other things, they are always insoluble. So lastly, even though we've already talked about this a little bit, hopefully you're more aware of the word stoichiometry. It's just talking about ratios. So the coefficients, which is the numbers in front of your equation, in the equation show that the relative number of moles react and are produced. So basically it's saying that when we look at our equations, we can use our mole ratios to figure out what we started with versus what we finished with. So the other thing that I really want to draw your attention to was this idea here, which is talking about limiting reagents and also things in excess. So just saying that if you have one substance that you have a lot of and another substance that you have very little of, the one that you have very little of will react with the one that is in excess, but then the reaction will stop because there's no more of that substance left to react. And so you've got to figure out in your two reactants, which one is your limiting reactant, and that determines how much the thing goes for, how long it goes for, pardon me. So, for example, we can see that we have our silver nitrate plus calcium bromide, and that should be an arrow, so I'll draw that in, goes to silver bromide and calcium nitrate. So in this case, when we've done a balanced equation, we have a 2 in front of our silver nitrate and a 2 in front of our AgBr, silver bromide. So it's saying that it's quite a badly thing, but that's okay. Sometimes formatting does not work, and that's okay. So perhaps the important thing to think about is that for every 1 mole you have of calcium bromide, you have 2 moles for silver nitrate. And then you can, if you're given the masses and you can figure out the molar mass for each of them, that means that you can calculate the number of mole and then convert. So step 2 is calculate number of mole for each. And then again, step 3, which just doesn't really work, is calculate 1 mole of each reactant based on the coefficient. So if we were looking at AgNO3 and CaBr2, we know that we have 2 moles for this for every one of that. So therefore, the number of moles that you end up with, you'd have to double. Now, you know that there's 2 reactant amounts can be compared. Which has the lowest value, that must be the limiting one. So in this case, silver is slightly lower with 0.044 versus the 0.05. I hope that's right. Yeah, that's right. And therefore, all of this will be used, and you'll be left with about 0.06, pardon me, mole of silver, of calcium bromide that doesn't react. And then we see step 4 is that the limiting amount is the one that you use to calculate everything, and that's then you've done your mole ratio times 2, and then you need to work out the quantity of the unknown. Okay, and then you just figure it out. So you're sort of starting at one side of the equation. You work out which has got more reactant out of the two reactants. Use that number to figure out your unknown for your product, and then you can work it through.